Here we take the universe to mean the region from which light has had time to reach us over its finite lifetime. It isn't a wall or a dome, but a limit of causal access, age plus the finite speed of light, define a sphere of observability. Beyond it, the cosmos may continue, but information from there hasn't arrived. Not because objects are absent, but because there hasn't been enough time for the signal to travel. Therefore, any sky map is an image of the interior of this sphere, not of everything that exists. The darkness of night points to a finite age. If time were infinite, light from an infinite multitude of sources would fill the entire field of view. So somewhere in the data there must be an echo of the beginning, not from stars but from the medium itself, when matter and radiation were still coupled. That echo has been found. The cosmic microwave background, CMB, an almost isotropic glow with a temperature of about 2.7 kelvins, arose when the overheated plasma cooled, electrons bound to protons and photons began to travel freely through an expanding space. We are not seeing a picture of galaxies, but the light released to the world at the moment it became transparent. The WMA Pan-Planck maps show an almost perfect uniformity of this background and microscopic brightness, deviations, tens of microkelvins. These variations are not instrument noise, but the primordial seed of future large-scale structure, where the background is slightly warmer or cooler. Galaxies and clusters later form. Therefore, the background fixes the initial conditions. It precedes the stars and passes through all of space as a universal field on which the subsequent history of matter is written. You can see the idea in an everyday example. With no broadcast, an old television shows snow. A small fraction of that static is a real detector response to the relic glow that fills the entire sky. The point of the illustration isn't the household detail, but the logic. This is not a local lamp, but an even backlight that both reveals the early scene and, like any backlight, partly hides the darkest corners, blocking a direct view into places where light has not yet been. Let's start with precise definitions. Meta-galaxy is a historical synonym for the observable region. We use it as a short label. Boundary here means the boundary of observability, set by time and the speed of light. The dark sky paradox is the logical incompatibility of infinite shining time with a dark night. The sensible way to resolve it is through age and light propagation, not by postulating arbitrary absorption everywhere. With these meanings fixed, we can test popular explanations without ambiguity and select the one that survives both the data on the cosmic microwave background, CMB, and the map of structure. We've pinned down the limits of the observable and the background near 2.7 kelvins. Now let's show where the logic clicks and reveals a flaw. Night is dark. This points to a finite age of the world. Then there should be an observable trace of the beginning. There is the cosmic microwave background, EMB, an almost uniform glow with a temperature of about 2.7 kelvins, which appeared after recombination, when photons decoupled from matter and began to travel freely through an expanding space. On the maps, the background is nearly identical, and the deviations are only tens of microkelvins. These fluctuations are the seeds of future structure, the places where galaxies later gather. The logic is consistent. Darkness is explained by age. The background records the beginning. So where is the snag? It is here. The background is a continuous backlight of the early state, uniform across the sky. It helps us see the past, yet it also limits any direct look beyond. A simple question follows. If we see this relic glow in all directions, can we look past it and see anything outside the observable region? In practice, no, we run into the surface of last scattering, a boundary beyond which light from earlier epochs carries no image of objects. We can read temperature in its tiny fluctuations, but not a picture of what lies before that. The edge our observations meet is set not by geography but by causality. The light has simply not had time. A second tension follows. If the background is so smooth, why is today's universe so lumpy, with galaxies, voids, and clusters? We need a mechanism that, first, makes the distribution nearly uniform in a very short time. Second, creates small but sufficiently seeding fluctuations for later growth of structure. Third, explains why we do not see a wall at the edge, even though a limit to what we can observe exists. One proposed answer is inflationary expansion, a very early, rapid growth of the scale factor that smooths irregularities and stretches quantum fluctuations up to cosmological sizes. Questions remain for the observer. If inflation really happened, why are some expected signatures hard to catch, and why does our visible region remain finite in light travel time? We return to the same limit. The boundary is not a rim of matter, but the end of available information. So the logical click is this: the dark night agrees with a finite age. The relic background confirms a hot early world and provides the seed of structure. But the same picture imposes a principled observational boundary. We see the beginning as a uniform field and cannot step past it with tools based on light. Therefore, we must test hypotheses inside this causal sphere, reconstructing conditions from the fluctuations, the CMB maps, and the distribution of matter. That is the task of the next round of checks. We've marked where the logic breaks. Now we'll test the competing ideas one by one, cutting away extra assumptions. It's all interstellar dust. If dust blocks starlight, the sky could be dark without invoking a finite age. But then the intergalactic medium would have to absorb enormous energy and heat up. Hot dust would re-radiate in the infrared and produce a bright background. Observations do show an infrared background, but far weaker than what would be needed to replace the light of the stars. So dust matters locally. Milky Way lanes nebula but doesn't solve the dark sky paradox as a whole. Total screening violates energy balance. Stars are just too sparse, so the total light is small. If sources were so rare that the sky thins out, deeper surveys should quickly hit emptiness as sensitivity improves. In reality, catalogs show the opposite. As depth increases, the number of faint galaxies rises in a regular way until cosmological dimming takes over because of redshift and the finite time light has to travel. Mere sparseness, without the time factor, doesn't match what we see. Light gets tired on the way. The tired light idea says photons lose energy with distance without space expanding. If so, spectral lines from distant galaxies would shift redward without time dilation, and supernova light curves wouldn't stretch. But we observe both the spectral redshift and stretched light curves signatures of expanding space. Tired light fails this check. An eternal, steady-state universe. If the cosmos is eternal and unchanging on average, the sky's brightness should diverge. No matter the transparency, ever more shells of sources pile on. The observed darkness demands a cutoff for the contribution of distant shells. A finite age and expansion provide that cutoff. Radiation from the far past hasn't had time to arrive, and what does arrive is stretched and cooled by redshift, reducing both the energy per photon and the photon arrival rate at the detector. A physical edge. A wall of matter. If a literal wall existed, maps of the background glow would show odd boundaries, and the distribution of distant galaxies would break geometrically. Instead, the pattern is uniform on average. The boundary we hit is causal, not material. The sphere is set by age and light speed, not by a rim of the world. Interim conclusion: dust cannot hide an infinite light field without lighting up the infrared source. Sparseness alone can't explain the steady rise in faint galaxies with depth. Tired light conflicts with observed time stretching. A steady state predicts a blinding sky, and no physical wall is seen. The working trio is a finite age of the observable region, expansion of space, and cosmological redshift. Together they suppress the contribution of the very distant sources and leave a universal trace of the beginning, and even glow near 2.7 kelvins. Next we'll ask where the tiny fluctuations come from and why they're enough to grow the structure we see today. Followed, we've narrowed the answer to a trio: finite age, expansion, and cosmological redshift. Now we must ask where the initial tiny ripples came from and whether they were big enough to grow today's structure. The problem is twofold. We need a source of the tiny irregularities in the early field, and we need to see why their amplitudes were sufficient within finite time to grow into galaxies and clusters. Maps of the cosmic microwave background, CMB, the nearly uniform glow at about 2.7 kelvins, show fluctuations of only tens of microkelvins. We take these as the seeds of future structure. It's instrument noise. If the variations were artifacts, independent missions wouldn't agree. In fact, successive maps line up and are reproducible. The observed roughness is a real property of the field, not a measurement error. Dirt on the beam, dust and late-time sources. If the pattern came mainly from absorption and re-emission along the way, the map would track the later distribution of matter and wouldn't be so isotropic. We see the opposite. The background is uniform on average, and its small deviations behave like an imprint of a very early state, the surface of last scattering, where photons began to travel freely. The amplitude is too small to grow. After recombination, radiation pressure drops and irregularities grow under gravity. The uniform background fixes the initial conditions. Gravity in an expanding universe amplifies them into the contrast we observe. Almost smooth field plus small ripples is exactly the starting configuration required. A generation mechanism without inflation. Inflation is a brief, extremely rapid early expansion that smoothed the distribution and stretched microscopic quantum jitters to cosmic size. Like dots on a rubber sheet, pull it hard. The dots fly apart and tiny ripples become a large-scale pattern, or like a faint whisper, stretched in time so the contour becomes audible. Skipping this phase is the just assume nice initial conditions approach. But then, 3 gaps remain. Why distant regions with no time to exchange signals share the same temperature? Why fluctuations are small yet everywhere? Why we see a universal last scattering surface rather than mismatched patches? Early rapid expansion answers at once. It smooths differences and lifts quantum ripples to the very tens of microkelvins we measure on the sky. Some expected signatures are hard to detect, and the causal limit is still set by time and light speed, but the observational logic of the CMB fits this picture. Interim takeaway: the fluctuations are not instrument noise or beam dirt. Their size matches gravitational growth after recombination, and their universality and isotropy are naturally explained by early rapid expansion. The working picture is an almost uniform early field, a universal last scattering surface, and small ripples that gravity amplifies into galaxies and clusters. Next, we'll combine the facts into one simple explanation and spell out what it predicts for observations. We found where the small ripples come from and how they grow. Now let's fold everything into one simple explanation. With a quick visual, early rapid expansion smoothed the universe and stretched tiny jitters into the pattern we see today. A finite age of the observable region, expansion of space, and cosmological redshift together explain 3 things: the darkness of night, the nearly uniform background near 2.7 kelvins, and the rise of structure from tiny fluctuations. If the lifetime is finite, not all light has had time to reach us, so distant shells don't flood the sky with endless brightness. As space expands, each photon is stretched, its wavelength grows, its energy per quantum drops, and the arriving flux weakens. That is how the early hot light became a cold microwave field, the universe's universal backlight. To see how smoothing works, a simple picture is enough. Imagine a rubber mesh with fine wrinkles. Stretch it many times over. The creases flatten, and individual points pull apart. The same with space. A brief phase of extremely rapid early expansion, inflation smoothed differences and stretched tiny quantum jitters up to galactic scales. Their imprint is what we now see on the sky as small brightness steps tens of microkelvins. When the plasma cooled, electrons bound to protons, the medium became transparent, and photons decoupled from matter, carrying a snapshot of that moment. The almost uniform temperature gives a smooth background. The small fluctuations are the seeds of future structure. After transparency, radiation pressure eases, gravity strengthens the slightly denser patches, and over time builds galaxies and the voids between them. The smallness of the initial differences explains why we don't see seams or walls on sky maps, only a gentle statistical pattern. Before transparency, frequent photon scatterings with charged particles erased any image. That is why the surface of last scattering is not a wall of matter but a boundary of information. Earlier than that, physics still unfolds, but there is no image that light can carry. We hit not a rim of the world, but a causal limit set by time and the speed of light. Why is night still dark, even with many stars? Because the contribution from the farthest sources is weakened to invisibility. Their light has not arrived, and what has arrived is shifted to longer waves and cooled. Instead of a blinding sky, we see an even microwave field, punctuated by points of starlight. Those three factors, finite age, expansion, and redshift, yield a coherent picture: darkness without imaginary curtains, a background near 2.7 kelvins as the imprint of transparency, and small fluctuations sufficient for gravitational growth. One linkage explains everything we observe. Next comes the quantitative side, what this scheme predicts, and how observations test it. The boundary our observations hit isn't material, it isn't a rim of the world, but a limit of information. Light from earlier epochs carries no images because before transparency photons scattered so often that any picture was erased. So talking about a geometric wall of the universe is misleading. The correct terms are the surface of last scattering and a causal sphere set by age and the finite speed of light. A dark night is the normal result of finite age and expansion. The distant shells of the sky don't blind us because nothing covers them, but because their contribution hasn't had time to arrive, and what does arrive is stretched and cooled into microwaves. The darkness itself is observational evidence for a hot, early universe, followed by expansion, not a flaw in counting stars. Maps of the cosmic microwave background, EMB, lock in the initial conditions for the growth of structure. Near uniformity plus tiny brightness steps, tens of microkelvins set the seeds from which gravity grows, galaxies, clusters, and voids. Large-scale structure doesn't contradict the smooth background, it follows from it, a small initial deviation, amplified by gravity after transparency. Method takeaway: to understand today's matter distribution, learn to read yesterday's fluctuation pattern. Everywhere the same has precise limits. We see an almost isotropic background, but the key is the almost. The small departures are the physics. What matters isn't the average temperature near 2.7 kelvins, but the spectrum and statistics of its tiny angular variations. Those hold direct keys to matter density, the expansion rate, and how growth preceded light. Looking further requires a different messenger, not just a bigger telescope. Light runs into the transparency boundary. So seeing earlier relies on indirect channels, the shape of fluctuations, the traces early processes left in today's distributions, and physics that can carry information before transparency. For example, gravitational effects reconstructed from background maps and structure. The practical rule for observers: boost sensitivity to microsignals and sharpen statistics, not chase a crack in the wall. One explanation ties three tiers of data: dark night, uniform background, and late-time structure. That's economy of assumptions, no imaginary curtains or rims needed. Finite age, expansion, and redshift together yield the microwave background, its small fluctuations, and the later gravitational growth. The picture closes by the logic of observations. We've laid out the theory's consequences, now let's check how instruments and observations back them up. The best thing about this picture is that it doesn't just explain, it predicts. If the cosmos is truly expanding, spectra of distant galaxies must shift toward the red in proportion to distance. Observations show exactly that. The farther the object, the longer the wavelength. Space is stretching. Light isn't merely getting tired. Second, the cosmic microwave background, CMB, isn't random mush, it's structured. A detailed look at the spectrum of its fluctuations reveals rows of acoustic peaks, the traces of sound waves in the early plasma. The spacing of those peaks matches calculations for matter density and the expansion rate. In other words, the map isn't just smooth, it carries its own barcode of physical parameters. Third, the way galaxies are spaced on large scales echoes the background statistics. In big surveys, we see the same characteristic wavelengths that appear in the CMB spectrum. That continuity means what began as tiny temperature ripples became the large-scale matter pattern. Fourth, the background is the same in every direction to within a few tens of microkelvins, yet a small anisotropy remains. It shows the solar system's motion relative to the average cosmos, letting us measure our galaxy's own speed at about 600 kilometers per second. The background thus provides a natural reference frame for the universe, not a privileged center, but a common backdrop for motion. Fifth, The background's temperature changes over time, the way expansion predicts. Measurements using distant quasars indicate that billions of years ago it was hotter by exactly the amount the expanding universe formula requires. That's a check in time, not just across space. Finally, modern cosmology runs simulations seeded with initial conditions taken from the CMB. Those models reproduce the observed distribution of galaxies and the statistics of clusters. It's a powerful test. A computer universe evolves like the real one when it starts from a temperature near 2.7 kelvins and fluctuations of only tens of microkelvins. These matches aren't coincidences. Each observation sharpens the parameters without breaking the logic. The theory that explained the dark night is now measured to microkelvin precision. Experiments back up every link in the chain. Now we need to mark where this picture stops working and where new ideas must begin. The sound traces of the early plasma. In the hot beginning, matter and radiation were coupled. Density waves behaved like sound. If space then expands smoothly, the cosmic microwave background, CMB map, must show characteristic scales, peaks in the fluctuation spectrum. The same measuring stick later appears in the galaxy distribution as baryon acoustic oscillations. In the probability of galaxy separations, a preferred step shows up. When two independent datasets show the same scale, the almost uniform start plus expansion hypothesis passes. The same physical ruler shows up in both early light and late-time matter. Time stretching in distant supernovae. If redshift is the stretching of space, ticking processes at great distance must appear slower to us. A supernova's light curve stretches by exactly the same factor as the wavelength. Type 1a supernovae are convenient clocks because their flashes share a similar shape. The observation is simple. The larger the redshift, the longer the same flash lasts. That separates true cosmological stretching from tired light. Not only the quantum's energy drops, the entire time pattern stretches. The imprint of galaxy clusters on the background. Hot gas inside clusters scatters passing background photons and boosts their energy slightly. This is the Sunyaev-Seldovich effect. On the otherwise even background map, tiny warmed spots appear exactly where massive clusters sit. The logic is hard-edged. If the background fills space uniformly, any local interaction must mark it like tracing paper. We do see cluster coordinates matching those spots, an independent way to see structure by how it affects the background rather than by its own light. These three examples probe different links of one chain. Acoustic scales confirm the initial conditions, stretched light curves confirm expansion itself, and cluster warming confirms the interaction of late-time structure with the universal field. The same rules yield consistent signals across eras and instruments. That's the strength of a simple explanation. Every theory lives inside its assumptions. Here are the big three. Limited observations, we can see only the part of the universe from which light has had time to reach us, over roughly 13.5 billion years. Everything beyond lies past the causal horizon. That isn't empty and it isn't the end of the world, it's simply unreachable. No signal has arrived from there. Even the sharpest CMB map is a portrait of the observable fragment, not of all that exists. Dependence on our model of matter and energy. Expansion and structure are described by general relativity and by the fractions of matter, radiation, and the so-called dark energy. Measurements pin those fractions down, but don't tell us what they are in essence. We can compute how much of each is needed to match observations, yet most of the matter and energy remain unidentified in nature. The framework works, but some ingredients are still undefined at heart. The timing of inflation itself, a brief, ultra-fast, early expansion explains uniformity in fluctuations, but lacks a direct, unambiguous fingerprint so far, such as primordial gravitational waves. Inflation is our best working explanation, not a finished fact. And then there's the light limit itself. Everything we know about the beginning is based on photons. We see the world by its glow. Before a certain epoch, light in the everyday sense didn't exist. To go earlier, we need other messengers, neutrinos, gravitational waves, or interactions not yet known. That's where the next step of knowledge begins, mapped out, but not yet crossed. To make the theory's boundaries sharper, let's look at the alternatives. Ideas that sound plausible, but fail when tested against observations. Steady-state universe. In this picture, the cosmos is eternal and uniform on average, with new stars added as old ones fade. At first glance, no need to talk about a beginning or an age. But then the sky should be blindingly bright. With infinite time, light from infinitely many stars fills all space. The observed dark night flatly contradicts this model. Tired light. Here, light loses energy with distance, so redshift needs no expansion. But if photons simply tired, they'd lose energy without stretching time. Supernova flashes observed at different distances would last the same length. In reality, distant flashes run slower. Time stretches just like the wavelength. That happens only in expanding space, not with tired light. A universe without inflation. One could assume it simply started smooth. No early, accelerated expansion. But then a core question remains. Why do sky regions separated by billions of light-years share the same temperature if they never exchanged light? Without an inflation phase, no information could spread fast enough to level conditions. Inflation removes exactly this paradox. A short burst of rapid growth spreads an already smoothed field across immense distances, preserving uniformity. A many-cycle universe, endless bang-crunch cycles sound symmetrically appealing, but there's no observational trace. The background we see matches a single hot episode, no signs of earlier cycles in its spectrum or temperature map. All these alternatives share one flaw. Each fixes part of the equation while breaking another. The hot, expanding universe with an inflationary phase remains the only picture in which the dark night, the microwave background, and the matter structure fit into a non-contradictory system, simple because it is logical. Now that we've separated the robust explanation from the failed ones, what does this picture change for us, for observers living inside an expanding universe? The main takeaway is simple. We don't live in a finished cosmos, but in a process that continues. Dark night, the smooth background, and redshift aren't three separate puzzles. They're three strokes of one image, an expanding universe of finite age. Every look through a telescope is a look back in time. When we see a galaxy billions of light years away, we see not what is but what was when its light set out. A plain consequence follows. There is no center or edge. Every observer has a personal sphere of visibility and a personal horizon. The cosmic microwave background, CMB map, becomes not just a sky picture but a calendar of the cosmos. It records the balance of light and matter from which everything else grew. We're not staring at leftover flame, we're seeing the trace of order, the imprint of the moment when physical laws first held steady. For us, here and now, this means the universe is not endless repetition, but a calculable process. We can measure its age, its rate of expansion, its matter density, and we can predict structure and temperature. Knowledge stops being a catalog of facts and becomes a tool, a way to see ourselves inside a system that is still moving and developing. The dark night isn't a miscount of stars, it's a trace of age. The smooth background isn't a curtain, it's the memory of when the world turned transparent. The fluctuations aren't noise, they're the sketch of future galaxies. The rules didn't fail, the wrong starting assumption did. Endless time. We live inside the proof. Light arrives late, space stretches, structure grows. One conclusion is enough: to see farther, first measure the limits of what can be seen. The picture rests on three parts: a finite age of the observable region, expansion of space, and cosmological redshift. Its strength is in testable bets. Here is what it promises, and what it risks. The background must cool exactly as an expanding universe dictates. It was hotter in the past by precisely the factor the scale of space increased. Any systematic mismatch breaks the age plus expansion link. The background's fluctuations must be almost but not perfectly scale invariant. Think nearly flat spectrum with a slight tilt. A big kink or deep dip would force a change to the starting conditions. Spatial curvature is near zero. If future measurements find a clear departure from Euclidean geometry on vast scales, early smoothing was different or absent. The fluctuation statistics are almost Gaussian. A strong non-Gaussian component would mean the seeding mechanism is more complex than small quantum ripples stretched by expansion. The same acoustic step must appear in both light and matter. Baryon acoustic oscillations, the scale read in the background spectrum, should keep showing up in deeper galaxy catalogs. If that step vanishes at new depths, the early light-late matter continuity breaks. Structure must grow at the predicted pace. Contrast in large-scale maps should rise over time according to a known law. If velocity and density fields keep disagreeing with that law, either the matter mix is off or the expansion dynamics are. A primordial gravitational wave trace may appear in polarization. A distinctive swirling pattern on the background would confirm waves from the earliest stage. If we reach the required sensitivity and still see nothing, whole classes of early scenarios are cut away. Subtle fingerprints of the universe's composition must agree across methods. The sum of neutrino masses and the amount of unseen matter blurs small-scale structure in specific ways. Background maps, weak lensing, and cluster counts must match. If they don't, a key ingredient is missing from the recipe. Bottom line, temperature over time, spectrum shape, near-zero curvature, Gaussianicity, the repeated scale in galaxy maps, growth rate, polarization, and fine-scale composition effects. A persistent, systematic failure on any one of these isn't a cue to tune the knobs, it's a reason to rebuild the assumptions. That is what real testability means. If the universe is stretching, why don't the planets drift off their orbits? Because the sun's gravity holds the solar system tightly. Cosmic stretching shows up on enormous scales, between far-flung galaxies. Why is night dark if there are so many stars? Not all light has had time to arrive. The universe's age is finite. And the light that has come from very far away has stretched and cooled, slipping out of what our eyes can see. Are we at the center of the world? No, every observer has a personal bubble of visibility. We see only from where light has had time to reach us. No special center required. That smooth microwave glow across the sky, isn't it dust? No. It's the light of the early universe, left over from when the cosmos turned transparent. It's nearly the same in all directions, with faint mottling, the tiny seeds from which galaxies later grew. Can we look earlier than the beginning with this same light? Not with light. Before transparency, scattering erased any picture. But we can hunt indirect traces, special polarization patterns in that glow, gravitational lensing, even very faint gravitational waves. It's like reading footprints in snow after the walker has passed. We started with a simple riddle. Why is the sky dark if stars are everywhere? We crossed backgrounds, expansion, tiny ripples, cooling, tests, and rival ideas. And suddenly, it was clear. Darkness isn't the absence of light, it's light's limit. So the question isn't for the stars, but for us. If everything visible was once invisible, what are we failing to notice until we cool enough to see it?